So we've looked at many statements now where we could trade a derivative in the bulk for an operation at the boundary. And here derivative is sort of in air quotes because it could be a curl, it could be a divergence. And so we have a broad it could be a gradient. So we have a broad notion here of derivative. And here I'm just summarizing all of these, and I'm giving you a view based on the dimensions. Okay, so if we have a 1D manifold, I call it a manifold, is just a line. Okay, a 1D manifold is a line, a 2D manifold is a surface, a 3D manifold is a sort of a volume. Okay, and a manifold is an abstraction of a surface, okay, to any dimension. Okay, a 1D but you could go higher than a surface, okay, and get a 3D manifold, 4D manifold. I mean, some people tell us that the universe itself is a 4D manifold where you have 3 spatial dimensions and 1 temporal dimension. Okay, or you could go down in dimensions. A 1D manifold is a curve. Okay, a 0D manifold is a point. Okay, and so if we have a 1D manifold embedded in R1 in 1 dimension, okay, then this sort of fundamental theorem is the fundamental theorem of calculus. Here we're trading the derivative in the bulk, in the interval AB, for an operation at the boundary, this subtraction. You just evaluate f here, and you subtract the evaluation of f there, okay? You could also look at 1D manifolds embedded in R2, okay? And there we got that the line integral, vector line integral of a gradient of a scalar function dr. You could either do this derivative, right, the gradient on just air quotes derivative in the bulk, or you could trade that for an operation at the boundary, taking the phi, the potential function, evaluating it at b and subtracting its evaluation at a. Okay, this could also be done for vector line fluxes. Okay, we also looked at line fluxes, and there you actually have, these only live in R2, a vector line flux. A higher notion of flux would have to live in R3. Okay, and so what we looked at there, okay, is so these were the derivative operations, and they were traded for an operation in the at the boundary. Just a quick note here about this one. All right, this also would work for a 1D manifold in R3, or in fact any dimension. Okay, but this one, no, this only works for vector line fluxes, and we only talked about it as living in R2. Okay, now what about 2D manifolds? Well, with 2D manifolds, we got Green's function, Green's theorem. And so here we have a curve living in R2 that bounds a region R, and you could trade the 2D curl in the region R for a vector line integral at the boundary, okay? Or we also looked at Green's theorem in flux form, and here you could trade a 2D divergence in R for a flux, okay, of the vector field in R2. Okay, this is a vector line flux that lives in R2. And we then went to 2D manifolds embedded in R3. That was 2D manifolds in R2. Now we then went one step further and embedded a 2D manifold, the surface, in R3. And there we got Stoke's theorem, which tells us that a line integral at the boundary C could be traded for the curl dot ds, so of flux of the curl around this surface, okay? And now this flux is the flux in the surface. If you're living in R3, the flux is defined in across a surface. In R2, it could be defined across a curve, but in R3, across the surface. And here's then the generalization of Green's theorem there. Okay, then we took it finally one step farther, and we looked at 3D manifolds. D, this volume, is a 3D manifold, okay? And here you could do the flux at the surface, or you could trade that for which derivative? The divergence in the actual volume, in the bulk. Okay, these are all these statements that are telling you you can trade a derivative in the bulk for an operation at the boundary. Okay, and we've done this so many times, we've seen it so many times. Okay, for all sorts of different manifolds embedded in other, manifolds that one starts to scratch their head and wonder, is this really a manifestation of a deeper fundamental truth? And it is. Okay, we have something called the Generalized Stokes theorem that you could derive any of these other theorems as a corollary to this. Okay, this theorem here, I'll spare you reading it out, as you need to use the language of differential forms. Okay, to really talk about it. But here it is, and it's telling you that the integral of this differential form at the boundary is equal to the derivative of that differential form in the bulk. Okay, so you could trade a derivative in the bulk for an operation at the boundary. Okay, and this generalized Stokes theorem, you need differential topology to get into it. In the US, that typically you get into that in the beginning graduate years, and it's one of the most beautiful theorems of mathematics, and you just saw many manifestations of it throughout this course.